Hello, Math 2. This is lesson 4, graphing piecewise functions. So piecewise functions are functions that are made up of little pieces of other functions. So I've got 3 examples on the board right now. So you can see this first one is made up of 2 pieces of a parabola. We've got this one and this one. We've got this middle function that has a piece that is a parabola, a piece that is a horizontal line, and a piece that is a diagonal line. And then we've got this last piecewise function over here that is made up of 3 pieces of lines. So piecewise functions are functions that are made up of pieces of other functions. So we're going to start by just graphing a piece of a function. So we've got function f of x equals x squared minus 3. So we see a power 2 in that function, so we know it's going to be a parabola U-shaped function. But we have this little restriction on our x values. This function is only valid or has a domain from -1 to 3. So we're just going to graph a piece of this parabola. Well, the way that you would graph a piece of a function is that you graph that function, but you only keep a section of it. So if I'm graphing this parabola, it has a vertex of 0, -3. So here's the vertex on the coordinate plane. And this parabola, it doesn't have a stretch, so it follows the regular 1, 3, 5 pattern of parabolas. So I'm just going to plot a couple little dots here. So if we were looking at the entire parabola, it would look something like this. But we aren't graphing the whole parabola. We're only graphing a piece of the parabola, and the piece is only from, the domain is only from -1 to 3. So any of the other parts of that function we would want to erase or just not graph in the first place. So I'm keeping everything that is between the x values of -1 and the x value of 3. Everything in between I'm going to keep. But everything that's outside of that domain I'm going to erase. So I'm going to erase this upper little part right here as well. So I graphed it just in that light gray color because I wanted to show the whole parabola at first, but this function that we are graphing with its restricted domain, on the right side, we need an open circle because of this strictly less than symbol. So we're going to have an open circle on this side, but on the other side, we do have the inclusion of the 3, so we're going to fill that in on this side. And our graph is kind of this little hook, I guess. It's like a little fish hook, kind of. Get rid of that. So here is our function f of x, which has a restricted domain from -1 to 3. So we're going to try another domain restricted function. So this function f of x is equal to x plus 2. I don't have a power here. I don't have an absolute value symbol. So this is just a regular line. The y-intercept of this line is 2, and the slope is that it's a slope of 1. So again, I'm going to graph this in just a nice light gray color, and then I'm going to think about the domain restriction. So the line has a y-intercept of 2, and the slope is up 1 over 1. So if I kind of just dot that out, I've got this line right here. Y-intercept of 2, slope of 1. Okay, well, our line that we want to graph, our function, has a domain of only x values that are less than 1. So we want to keep all of the x values, or we want to keep all of the parts of the function for values of the domain less than 1. So we want to keep this entire left-hand side of the graph, but anything that is outside of that domain, anything over here on the right side, we want to erase away. So now that I've thought about that domain, I'm going to draw the graph in a little stronger. This is strictly less than 1, so it's going to have an open circle over here on this side, and then I'll sketch in that rest of that line. Wow, I don't know why it's wavy. I can't draw. Okay, and then I'm just going to go ahead and pull that highlighting away so you can see the graph. So we've got a piece of a line here. All right, so when we have a piecewise function, the way that the equations are written is with a couple of rows like this. So we've got our function is equal to, we have a brace symbol that is telling us that it has those two different pieces. The top piece, x plus 2 for x less than 1. We just graphed that a second ago. So I'm going to just flip back to that graph. So that was this piece of the line. So I'm going to go ahead and sketch that in. It had, let's see, it had its boundary. I'm just going to go back and just double check. Yep, the boundary was at 1, 3, and then it's got a slope. The slope is up 1/1 from left to right. So it kind of feels like it's negative, but if we think about it from left to right, it is a positive slope. So let's see. So it's like this. So that is this first piece of our graph, but our function has a second piece as well in this case. So it also has a section of the graph that is defined for x is greater than 1. So I have my coordinate plane shaded for blue for that part of the function. So this has a power of 2, so it's a parabola. The vertex of this parabola is at 1, 0. So the vertex, and I'm going to graph this again in a light gray because I'm going to end up having to erase part of it. 1, 0 is right here. This is a parabola that gets shifted horizontally 1 unit to the right. It doesn't have a stretch, or it's just a basic 1, 3, 5 parabola. Now I could dot this side of it, but in a second I'm going to have to erase that because my parabola is only defined on this blue section of the coordinate plane. This is a filled in circle because of the inclusion of the 1. And so my parabola is going to look like this. Oh, my hands are like shaky today or something. I can't graph very well, sorry. So this is what our piecewise function looks like. It has one piece that is a line, and it has one piece that is a portion of a parabola. And, I used that shading on the coordinate plane to help me see which side was on which, but this is maybe what it would look like without that shading happening. Again, the parabola is on the portion of the coordinate planes for x greater than 1, and the line is on the portion of the coordinate plane for x less than 1. All right, let's try another one. G of x also has two pieces. The boundary here is happening at -2. So the function looks like an absolute value or a V shape for x's that are less than or equal to -2. So this is going to be a V shape. The vertex of this parabola is going to be at -4, 0. So if I think about what that is going to look like, my vertex is right here. We don't have any kind of stretch happening, so this is just a regular up 1/1, and you could graph it the whole thing out if you want, but then bear in mind that boundary. This graph only has that shape for x's that are less than -2. So anything that is over here on this blue side of my coordinate plane, I need to erase. On the boundary, we have our inclusion happening. So right here, and then I'll just sketch in that V shape. Okay, so that's our first piece of the graph. The second piece has just a 3. So sometimes when it's just a number, it gives people a little bit of problems. This is the function is equal to 3. That's like thinking about y is equal to 3. This is a horizontal line. So again, I'm going to kind of graph it in gray. Here's the y value 3. So we're talking about this horizontal line that would go all the way across, but for our function, it only takes on that shape or that value for x's that are greater than -2. So it's not going to go extending into this yellow side. It's only going to be on this blue side of the coordinate plane for the x values that are greater than -2. So I'm going to go ahead and erase away these little marks because I don't need them. They are not part of my function. So here's our function g of x. It's got a piece that is a v shape and it has a piece that is a horizontal line. Now you might remember something called the vertical line test. The vertical line test is a way of testing if something is a function, and you can sort of think about mentally passing a line across that function, and it should never touch the function at more than one spot. For something like this boundary right here, you can only have one filled in circle. One of them, if they are stacked like that, one of them has to be open. So you can check to see if you've graphed it right by doing a quick sort of mental vertical line test. So if you made an error, for example, if you had extended this too far, then when you did that sort of mental vertical line check, you would have caught it and said, oh, wait, it's touching in two spots. That can't be right. And maybe be able to correct your error. Okay. Let's try another one. Now, I've not put the shading on the coordinate plane here so that we'll have to start thinking about our boundary a little bit more. So we've got function h of x. H of x is, again, two pieces. So we've got 2 times x minus 3 squared. So that is going to be a parabola shape, right? It's got a power of 2, so it's going to be a parabola. The vertex of this parabola is at 3, 0, and it has a stretch factor of 2. So I'm going to plot that in gray. 3, 0 is my vertex. My stretch is 2, so that's up 2 over 1. Up 2 over 1. And then the next one would be 6. 2, 6, 10. That's the 1, 3, 5 pattern that's been doubled by that stretch. So up 2 and then up 6. So we've got this U shape, but this is a piecewise function. So we only want to keep a portion of that graph. So you can think about, if you want, you could even highlight if you want the boundary. So our boundary is happening at 4. So this is where it needs to switch from one type of graph to another. So the parabola is for x values that are less than 4. So we're going to keep everything that is to the left of that boundary. And on the boundary, we have a filled in circle. So this is going to be filled in, and we'll keep this left-hand side. Anything else from the parabola, I need to erase away. All right, let's look at the other side of that function, the other piece. So for x's that are greater than 4, the shape of our function is a 1/2 x. Well, that is a line, and that line has a slope of 1/2, and the y-intercept is 0. So again, I'm going to graph that in a very light gray. So it's going right through the origin, a y-intercept of 0, because we don't have a number added at the end. Or if we sub in 0 for x, we get a y value of 0. And we're going to count off the slope 1/2. Up 1 over 2, up 1 over 2, up 1 over 2. And so it's this line. Now we only want to keep a portion of that line. We only want to keep a piece of it, the piece where x is greater than 4 with an open circle on the boundary. Now if I draw an open circle, it's actually in the same spot as that closed circle. So in other words, you can't even see that there's an open circle there because that closed circle is like filling the hole. Like you have a hole, but it gets filled in. So that's the same as having a closed circle. When your pieces connect, like this one does, you have that happen where it just is a connection and there's no open or closed circle. It's just connected. So in our other examples, we had sort of a jump happening. You can have a jump, but it can also connect. So we only kept the right-hand side of that line, so I need to erase away all of the other parts of that line. I got a little bit of my parabola there too. And so this is what our function looks like. I'm going to go ahead and move that highlighted boundary away because we don't need that there. If you want to highlight a boundary or something, you can. Try not to make it look like it's part of the function. Like you don't want to have this like weird vertical line here. So if you do something like draw that boundary to help you, either do it very lightly as a dashed line to just as a reminder to you, or with a highlighter would be fine as well. All right, there's one for you to try. I'm going to graph it just really quick in case you want to pause, try it, and check your work. So we've got the function negative. The first piece is -3, which is horizontal line for x is less than 1, included on the boundary. So should have this piece. And then a parabola that has been reflected. I need to graph this one in gray. The vertex is here at 4, and it's going to go down 1, 3, 5. So it starts for x is greater than 1. So we've got an open circle there. So we just have a very kind of very far side of that parabola. So this is what that would look like. Oh, this one's fun. I'm going to graph it. I like it. So our first piece is a line. It's got a slope of 1 and a y-intercept of 0. So it looks like this. The boundary for that is happening at 0. So our piece is only for x values that are less than 0, less than or equal to 0. So filled in circle, and we're keeping the left-hand side. And then on the other side, we have a parabola shape with the vertex at the origin. So that would look like this. And we are only keeping the portion of that parabola where x's are greater than 0. So we would just keep this side. So this one is a connected one. Okay, so we want to talk a little bit about step functions now. Step functions are functions. They're called step functions because they look like steps. They look like a bunch of little horizontal pieces. And they might go up like steps, but they also can step up and down, or they could do something weird like this, but all of the pieces are little bits of horizontal lines. So this function has 3 steps to it. The first step has a height of 4. So that would be, if it was just this, y equals 4, it would be this whole line up here. But we only want to keep a piece of it between -4 and -2 is the domain of that piece. So filled in circle on both sides of that piece. From -4 over to -2, this little piece. So any other portion of that line I would want to erase away. The next step, or the next piece of the function, has a height of 2. So that's here. We're keeping the domain of this piece is from -2 open circle to 2 open circle. So -2 to 2, and just keep that section in between. So this is a longer step. They don't have to have the same width. Sometimes they do, but they don't have to. And then our last step, our last piece, has a height of -3, way down here. The domain for this piece is from 2 to 4, and these are closed circles on both sides, from 2 to 4. So there's our last piece. So this is what our function looks like. It's called a step function because all of the pieces are flat. So here's one for you to try if you want to pause and try it and see how you do, and I'll graph it. You can check yourself. For the first piece, -1 between, let's see, closed circle to open circle. Here we go. The next one would be a height of 1, and it's between -1 and 2. And the last piece goes back down to -1, filled in circle at 2, open circle at 5. So this is what that function should look like if you tried it. Okay, so we're going to evaluate some piecewise functions now. When we're evaluating, we want to sub an x value into the function. So if I wanted to evaluate f of x equals x plus 2, I would just sub in that number. The trick with piecewise functions is that because you have more than one part, you don't sub x into both parts. You have to use the boundary, use the domain pieces to figure out which part to use. And once you decide which part to use, you only sub into that piece. So if I wanted to evaluate f of 10, right here, this first one, I have to think about, is 10 less than 1 or is 10 greater than 1? And 10 is greater than 1. So I would use the blue section or the blue piece of that function. So it would be 10 minus 1 squared. That's 9 squared. That's 81. For f of 0, I have to think about, is 0 less than 1? Thinking about this piece, or is 0 greater than 1? Well, 0 is definitely less than 1, so we would use the yellow piece of the function. So it would be, whoops, I guess I don't really need a parenthesis there. It would be 0 plus 2, which is 2. So I'm not subbing in the 0 to the second part. I'm only subbing in the 0 into the first part. The last one is f of 2. So again, thinking about our boundary and our two domains, 2 is greater than or equal to 1. So I'm going to use that second piece. So this would be 2 minus 1 squared. So 2 minus 1 is 1. And if we square that 1, we get 1. F of 4. 4 is also greater than 1. So I'm going to use the second piece again. 4 minus 1 squared. That's 3 squared, which is 9. F of -3. Well, -3 is a number that is less than 1. So we would use the first piece here. -3 plus 2 is -1. And finally, f of -9. Well, -9 is definitely less than 1. So again, we would use that second piece. So that's -9 plus 2, which is -7. So you have to think about which section of the domain that x value belongs in, and then you will use that piece only to evaluate. All right, now we're going to just finish up by writing a couple of equations if we are shown the graphs. So we're going to do 2 of these. These can be a little bit challenging to write. So this graph that we're looking at right here has 2 pieces. It has one piece that's a parabola and one piece that is a straight line. So when you have a piecewise function, you have your function name equal to, you have a brace, and then this one's going to have 2 rows. So we've got 1 row for our parabola and 1 row for our line. So we're going to start with the parabola. This parabola has a vertex of 0, 1, and it looks like it's just a regular stretch of 1, 3, 5. So that would be x squared plus 1. Our domain, our boundary, where it switches between the 2 pieces is occurring at 2. So I'm going to leave that line there. So when I think about the domain of that parabola, it is only for x's that are less than 2. So everything to the left of 2. And it has an open circle right there on the right-hand side. So that's going to be a strictly less than domain. The line here is a little bit tricky to write. When we write a line equation, we want to write it as mx plus b in slope-intercept form. The slope we can count off easily enough. This is going down 1 over 1, so that's going to be a -1. But the y-intercept is a little tricky here because the line gets cut off, so we don't see the y-intercept. So I need to extend it back and see what the y-intercept of that line is, and it is a 9. So it's going to be a +9 at the end. So that's -x plus 9. You can put a 1 in front of the x if you want. Now, the domain of that is the x values that are greater than or equal to 2. It asks us to evaluate, so I'm going to erase some of my sketching over here so we can do these 2 evaluations from the graph. If I'm evaluating from the graph, I just find that x value, -2, and see what the height of the function is. So f of -2 is 5. Again, I don't think about the line because I'm only just thinking about which piece is in that domain. F of 1 would be 2. All right, last one. We're going to draw or write the equation of this graph. It has 2 pieces. We've got a straight line right here. We could technically write this as 3 pieces, 3 separate lines, but we can write this section as an absolute value if we want. So we've got a line and we've got an absolute value. For the line, we need to count off the slope, and it looks like this slope is 1/3. So the equation of that line, and again, I've got to think about the y-intercept. The y-intercept would be 5 if it was extended over. So this line is 1/3 x, so it's the slope times x plus the y-intercept of 5. Our boundary is happening at -3, so this is for the x's that are less than -3. Our absolute value function has a vertex of 0, 1, so it's shifted up 1, and the slope of it is just up 1 over 1. So this will be absolute x, no stretch needed in the front, plus 1. The boundary of this is for x's that are greater than -3. Now, when it's connected like this, you can decide whether to include on the top or the bottom. It's really your choice. It doesn't really matter. I'm going to go ahead and include it right there. You probably wouldn't want to include it on both, though, just one or the other. All right, that is it. Thanks so much for watching, and let your teacher know if you have any questions.